Welcome to this presentation on C++ unordered maps. In this video, you will learn about fast hash-based key-value containers with standard unordered map. So, what exactly are unordered maps in C++? A standard unordered map is a container that stores key-value pairs in a hash table. This structure provides fast access to elements by their keys. Key features of unordered maps include a hash-based implementation, which gives you an average lookup time of order of 1. They do not guarantee any specific order of elements. Keys within the map must be unique. Unordered maps are part of the C++ standard template library, often referred to as STL, and have been available since C++ 11. In this diagram, you can see how key value pairs are stored. For example, the key apple points to the value 5, banana points to the value 8, and so on. Each key is unique and maps to a specific value. To start using unordered maps, you first need to include the appropriate header file. Add the line #include unordered_map to your C++ code. You will typically also want to include IOStream and string headers for input, output, and string manipulation. Here's how you can create unordered maps. To declare an empty unordered map with string keys and integer values, you would write standard unordered map, then within angular brackets specify string int, followed by the name of your map, in this case user scores. To initialize an unordered map with values, you can use an initializer list, as shown here with the fruit prices map. Please note that the unordered map template requires two type parameters, the type for the keys and the type for the values. Let us explore some basic operations you can perform with unordered maps. Here is how to insert elements. You can insert elements into an unordered map using the square bracket operator, the insert function, or the inplace function. Each of these methods adds a new key value pair to the map. To access elements, you can use the square bracket operator, the @ function, or the find function. The @ function will throw an exception if the key is not found, while find returns an iterator to the element, or standard end if the key does not exist. To check if a key exists in the unordered map, you can use the count function, which returns 1 if the key is found and 0 otherwise, or you can use the find function. Also, the contains function is available since C++ 20. To remove elements, you can use the erase function, either by specifying the key or by providing an iterator. To remove all elements from the map, use the clear function. There are several ways to iterate through the elements of an unordered map. Starting from C++ 11, you can use a range base for loop to iterate through each key value pair in the map. Each pair can be accessed directly within the loop. Since C++ 17, you can use structured bindings to directly unpack the key and value from each pair in the loop, making the code cleaner and more readable. Always remember that the order of elements in an unordered map is not guaranteed to be the order in which they were inserted. Now let's discuss the performance aspects of using unordered maps. In terms of time complexity, on average, lookup, insertion, and deletion operations take constant time order of 1. However, in the worst case, these operations can degrade to linear time order of n, typically when there are many hash collisions. Several factors can affect the performance of unordered maps. The worst-case performance occurs when many elements hash to the same bucket, leading to collisions. Also, performance tends to degrade as the load factor, which is the ratio of the number of elements to the number of buckets, increases. To optimize performance, you can reserve capacity to avoid rehashing, which happens when the map needs to allocate more buckets as it grows. Also, you can control the load factor to balance memory usage versus speed. A lower load factor increases the number of buckets, which can reduce collisions but increases memory consumption. Finally, you can use custom hash functions for complex keys to ensure a more uniform distribution of elements across buckets. Unordered maps are not limited to built-in types like integers or strings. You can also use custom types as keys, but this requires a bit more work. To use a custom type as a key, you need to define the following. First, create your custom struct or class, for example, a struct named point, with integer x and y coordinates. Next, you must overload the equality operator, that is, the double equals symbol, to define how two objects of your custom type are compared for equality. This is essential for the unordered map to determine if keys are identical. You also need to provide a hash function for your custom type. This involves specializing the standard hash template for your custom type within the standard namespace. The hash function should take an object of your custom type and return a size_t value, which is used as the hash code. For custom key types, it is very important to provide both an equality comparison operator and a hash function. The hash function should distribute values evenly to minimize collisions and maintain good performance. Let us look at a practical example of using unordered maps. A common problem is to count the frequency of words in a given text. An unordered map is particularly well suited for this task because it provides fast lookups and updates. In this code, the count word frequency function takes a string as input. It uses an unordered map to store each word and its count. It iterates through the text, splitting it into words, and increments the count for each word in the map. Finally, it displays each word along with its frequency. It's useful to compare unordered maps with other containers to understand when to use each one. Standard unordered map offers an average time complexity of order of 1 for lookups and insertions, but it does not maintain element ordering and has high memory usage. Standard map provides ordered iteration with a lookup and insertion time complexity of order of log n and medium memory usage. Standard vector of pairs has a linear time complexity for lookups, but constant amortized time for insertions. It maintains ordering if sorted and has low memory usage. Standard array of pairs also has a linear time complexity for lookups and the memory usage is the lowest. It also maintains ordering if sorted. So choose standard unordered map when you need fast lookups by key and do not care about element ordering. Use standard map when order matters or when you need range-based operations. Here are some best practices to keep in mind when working with unordered maps. Reserve capacity in advance when you have an idea of how many elements you will be storing. Use in place instead of insert to avoid unnecessary copies of objects. Before accessing an element using the square bracket operator, check if the key exists using find or contains to avoid creating unwanted default constructed values. Always provide good hash functions for your custom types to ensure efficient performance. Finally, consider using standard map if element ordering is important or if you need range operations. To summarize, standard unordered map offers fast average case lookups, insertions, and deletions with a time complexity of order of 1. It does not guarantee any element ordering. It typically has higher memory usage compared to ordered containers. Standard unordered map is perfect for tasks such as frequency counting, caching, and fast lookups. It has been available since C++11, with further improvements added in C++17 and C++20. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.